Dear viewers, myself Kashmiri Dass, lecturer at Government Polytechnic College for Girls, Patiala. Today my topic is stress and strain. Under this topic, I will discuss the various types of strains and stress, and also stress strain curve of mild steel specimen, and the deformation of find the deformation of the var under axial loading. We calculate the axial deformation due to load acting on the var. We consider rectangular vars, tapered vars. So, I will discuss one by one. So, under this topic, first of all, I will introduce you stress and strain. First is stress. Stress, before defining the stress, I will define the term elasticity. Elasticity means when a number of force acting on the body will deforms. The body will deforms due to force acting on it. The body regain its original shape after the removal of a force. That the body regain its original shape due to the internal resistance offered by the body. This internal resistance offered by the body per unit cross sectional area is called as stress. So, stress means direct stress under direct load. Direct stress means it is denoted by letter sigma. So, when a force is applied to an elastic body, the body deforms. The way in which the body deforms depends upon the type of force applied on it. Due to removal of forces on the body regain its original shape. This phenomenological process of the body is called as elasticity. So, stress depends upon the force acting on the body. So, in other terms, the internal resistance offered by the body per unit cross sectional area is called as stress. So, let see in the picture, F is the force acting on the body. That means that force makes the body shorten. If the body shorten in length, it is called as compressive force. Let us see in the picture. So, x is the amount in which the body shortens. So, L is the original length of the body, A is the original cross sectional area of the body. So, if the body shorten, so it is called as compressive stress. If the body longers in length, it means extension of the length of the body due to force acting on that. This force is called as tensile force. Let us see both of figures shows that compressive force and tensile forces. So, in the tensile force acting on the body in the bottom diagram. So, F is the force acting on the body, this is the pull force means tensile force. So, x is the distance, increase is due to force acting on the it. If area is the cross sectional area of the body, L is the original length of the body. If the body extends in length, so it means tensile force acting on the body. So, the stress is denoted by sigma. In simple terms, force per unit area is called as stress. So, means force, mathematically force is equal to stress is equal to load over area. Load means force acting on the body. So, another tensile and compressive forces are also called direct forces. Stress is the force per unit area upon which it acts. Mathematically, stress, it is denoted by sigma is equal to force over area, F over A. So, its unit is Pascal, or Pascal means Newton per square meter. So, 1 Pascal is equal to Newton per square meter. So, sigma means the stress is denoted by letter sigma symbol. So, in most of engineering fields, the stress has abbreviated as sigma or small p. So, its unit in the engineering field, the stress is measured in kPa, kilopascal, MPa, megapascal, GPa gigapascal. Pascal means Newton per square meter. Simply the stress, the unit of stress is Newton per square meter or Newton per square mm. So, simply the stress is force per unit area. So, I define the stress. Stress is defined as the strength of the material. Stress is defined as the strength of material per unit area or per unit strength. So, it is the force on a member divided by the area. Force means load acting on the body or a member. So, it is the force on a member divided by area, which carries the force formally expressed in psi or now in Newton per square mm or megapascal. Mathematically, stress is denoted by sigma is equal to force over area. Force is denoted by letter capital P or area is capital letter A. In this formula, stress is equal to force over area, where P is the applied normal load in the Newton and A is the area in square mm. The maximum stress in tensile or compressive occur over the section normal to the load. It means that tension force, tensile force or compressive force, which is always acting normal to the surface. So, simply the stress is force per unit area. So, let us see what is the normal stress. Normal stress means load is acting normal to the surface. So, it means normal stress is either tensile stress or compressive stress. It means member subjected to pure tension. Pure tension means tensile force is under tensile stress, while compressive members, that means members subjected to compressive force, that are called compression member. Here is tension member and compression member. The member which is subjected to tensile force is called as tension member. The member which is subjected to compressive force is called as compression member. So, it means member subjected to pure tension is under tensile stress, while compression members subjected to compressive force are under compressive stresses. Compressive force will tend to shorten the member. Tension force on the other hand will tends to lengthen the member. It means due to compressive force, so it increases the length of due to compressive force it decreases the length of the member. Due to tensile force it increases the length of the member. You see in the picture. So, first bar is under tension, means pull force, tensile force, P is the tensile force. So, it means this member is under tension. So, on the other side picture, right side, so P is compressive force acting on the bar. So, it means this bar is under compression. So, I define what is direct stress. Direct stress is denoted by letters psi, the epsilon. In each case, a force if is produced a deformation x. Due to force acting on the body, our deformation is x. In engineering, we usually change this force into stress and the deformation into strain, and we define these as follow. So, first of all, strain is the deformation per unit of the original length. So, I define strain. Strain means change in the length means deformation. Change in the length over original length is called as strain. The symbol epsilon, it is denoted by symbol epsilon. Strain is denoted by abbreviated as epsilon symbol. So, in other words, the strain in any direction is equal to change in dimension over original dimension. So, strain has no units since it is a ratio of length to length. Strain means no units, means change in length over original length. Both units are of length. So, strain has no units since it is the ratio of length to length. Most engineering material do not stretch very much before they become damages. So, strain value are very small figures, the values are very small in nature. It is quite normal to change small numbers into the exponent for that is micro strain 10 to the power minus 6, because strain has very low value in nature. So, basically strain has no units. So, and due to load acting on the body, very small strain is noted. So, another I define the term modulus of elasticity. Elastic material always spring back into shape when released. They also obeys Hooke's law. Hooke's law means stress is directly proportional to strain, obeys the law of elasticity. So, that means elastic material always spring back into shape when released, because when external forces acting on body is removed, then the spring back into original shape, because they also obey Hooke's law. So, this is the law of spring which states that deformation is directly proportional to the force. Here deformation means strain is directly proportional to the stress. So, according to Hooke's law, stress is directly proportional to strain. It depends, if this law of spring, it depends upon the stiffness of the spring. So, stiffness means force over deformation, that is called as stiffness. If the force acting on one axis and the deformation on the other axis, so the curve is straight line. So, straight line curve means stress is directly proportional to strain. This stiffness of the spring is different for the different material and different sizes of the material. We may eliminate the size by using stress and strain instead of force and deformation. We use the terms here, we use the term stress and strain instead of force and deformation. F and X is referred to direct stress and strain. Here F is the direct stress and X is the first of all, this is the deformation. So, we call it as a strain, then the force is equal to stress into area. So, stress into area. So, that means stress is equal to force over area. So, according to Hooke's law, stress is directly proportional to the strain. So, and on the other side, the stiffness is now the terms of stress and strain only. This constant is called as modulus of elasticity. So, modulus of elasticity from the law of Hooke's law, stress is directly proportional to strain and stress is equal to constant into strain. This constant is called as constant of proportionality and is also called as coefficient of elasticity and is known as modulus of elasticity. In other words, it is called as Young's modulus of elasticity. So, Young's modulus is equal to stress over strain. Young's modulus is equal to stress over strain. Its units are the same as unit of stress, because of this is equal to Young's modulus of elasticity is equal to stress over strain. Strain has no units. So, Young's modulus of the same elasticity has the same unit of stress. So, a graph is plotted between stress and strain and this graph comes out to be straight line, because stress is directly proportional to strain according to Hooke's law. So, that means a graph of stress against strain will be a straight line with the gradient of Young's modulus of elasticity. So, I define another term, ultimate tensile stress, means if a material is stressed until it breaks, means up to the maximum value. So, material is stretched up to the maximum load until it breaks, the tensile stress has reached the absolute limit, and this stress level is called the ultimate tensile stress. That means the specimen takes the maximum stress under loading. That stress is called as ultimate tensile stress. So, I then uh, explain the stress strain diagram. So, if any material, that means any specimen of any material, is loaded and tested uh, under universal testing machine, that is tensile or compressive machine, here we calculate the stress and strain and graph is plotted. So, this graph shows between stress and strain. So, here on y axis it is stress, on axis it is strain. So, O is the region where two axes of stress and strain meets, means O is region, the graph originated from the region. So, let us see in the picture in this stress strain diagram, from O to A the curve is straight line, curve is straight line. It means up to point O to A, that is up to point A, stress is directly proportional to strain within elastic limit, and then curve goes to from A to B. So, at point A we call it is proportional limit, that is elastic limit. That means the material regain its original shape after removal of loading. So, point A is called as proportional limit, that is elastic limit point, and then small increase in the load and very small increase in stress. So, that point B is called as yield stress point. So, up to point B we call it the yield stress. So, the material of any specimen yields under loading from B to A. So, B is the upper yielding point, A is the lower yielding point, and then graph goes from B to C. So, this is equivalent to constant straight line. So, this it means the mutual adjusting of particle in this material. So, and then goes on increasing under loading. So, D, at point D, this is the maximum point here, the maximum load taken by the material. So, that point is the ultimate point. So, stress at that point is called as ultimate stress, or it is called as maximum stress point. After that point D, when at point E, the material, that means specimen of any different material fails, that is fracture. So, its failure takes place. So, here is load is decreasing. So, it means, so this is called as breaking point. So, stress at this breaking point E is called as breaking stress. So, on this graph from O to E, so first of all the graph O to A is straight line. This is called as linear region. Linear region means stress is directly proportional to strain. That means stress strain relation should be linear in the nature. So, from point B to C, this is a perfect plastic or yielding of the specimen takes place. So, from B to C, this is the perfectly plastic in the nature. So, after that point C to D, this is the strain hardening. This curve is called as strain hardening point. So, in which the strain is hardening, and it take the maximum load at point D, and after from D to E, so failures takes place, the load is decreasing, calculated checked from the gauges, and at this failures takes place. So, from point D to E, this is called as necking of the material. So, this is the stress strain curve. In the following section, I will discuss the stress strain curve of mild steel specimen. Stress strain diagram. From this stress strain diagram, I will discuss first of all elastic behavior. why the material have elastic behavior. Under this, the curve is a straight line throughout most of the region under elastic behavior. Under elastic means within elastic limit, stress is proportional to strain. The material always obeys Hooke's law. It means material to be linear elastic, and the at point from O to A. So, I will earlier discuss this. So, this is a proportional limit point, means upper limit to the linear line. The material will respond elastically. The curve tends to bend and flattened out. So, and then I discuss the elastic limit point. Elastic limit means upon reaching this point, if the load is removed, the specimen still returns to the original shape. It means due to the removal of load, the specimen regain its original shape. So, this point is called as elastic limit point. So, I will discuss yielding of the material. At yielding point, a slight increase in stress above the elastic limit will result in breaking down of the material and causes it to the deform permanently. So, this is called as yielding. So, at this behavior of the material is called as yielding. So, the stress at that point cause yield stress at a rate of yield point, at the point of yield. So, the stress at the yielding point is called as yield stress. So, it is at the yielding point the plastic deformation also occurs. Once yield point is reached, the specimen will elongate, that means strain occur without any increase in load at the yielding point. So, material in this state is always perfectly elastic. So, up to the yielding point, the material is always elastic in nature. So, at the strain hardening point from the stress strain diagram, at this strain hardening stage, when yielding has ended, further load applied, resulting in a curve that rises continuously. So, after the yielding point, if further load is applied, resulting in a curve that rises continuously, and curve becomes flat, that is straight line when reaches ultimate stresses. The rise in the curve, it means strain hardening. While the specimen is elongated, its cross sectional area will decrease, and this decrease is of the specimen always fairly uniform. So, after the strain hardening stage, the stage comes necking. At the necking stage, the failure of the specimen takes place. So, at this stage, at means at the ultimate stress, the cross sectional area becomes its localized region of the specimen. It is caused by slip planes formed within material. So, at this stage, actual strain produced by the shear strain, I will discuss later on. As a result, neck tend to form in the specimen. So, this is called as necking stage of the specimen. At this stage, the failure of the sample takes place. So, smaller area can only carry lesser load, hence curve downward. So, at this stage, the specimen breaks at this at some stress or at some load. So, where the curve material breaks, so the stress at the breaking point is called as breaking stress. So, I will discuss stress strain curve for a mild steel specimen, and the specimen of mild steel is tested under universal testing machine, and the stress and strain observations are noted, and the curve is plotted, stress along the x axis, strain along the y axis, and the curve I will show you a curve. This is the stress strain curve of the mild steel specimen. So, I will earlier discuss this stress strain diagram. Similar is this. So, at this curve, so first of all from O to point P, so this is called as curve is straight line. This is called as proportional limit point, that is elastic limit point, and then other point cross means E, that is elastic limit point, and then the body will be yielding the specimen will yield, this is yielding point, and then curve goes higher to higher, gains the ultimate strength. So, at the this stage is the ultimate stress. So, and then the curve breaks. So, and this is called as rupture strength. So, breaking strength, breaking stress of the point. So, this is the stress strain curve of the mild steel specimen. So, first of all, I in this stress strain curve, first is proportional limit, that is elastic limit. So, this at this stage always weighs Hooke's law. So, from the origin O to the point called proportional limit, and the stress strain curve is straight line. This linear relation between elongation and the axial force causes first notified by Sir Robert Hooke in 1678 and is called Hooke's law, that within the proportional limit, that means elastic limit, that means stress is directly proportional to the strain. So, this Hooke's law given by the Sir Robert Hooke in 1678. And then I from this curve define the elastic limit. The elastic limit is the limit beyond which the material will no longer go back to the original shape when the load is removed, or it is a maximum stress that may be developed such that there is no permanent or residual deformation when the load is entirely removed. It means in this region at this point stress is directly proportional to strain. The curve is straight line and this in this region. So, and then that elastic limit is the limit beyond which the material will no longer go back to the original shape when the load is removed. So, this is the elastic limit. At up to the elastic limit, stress is directly proportional to the strain. So, on the curve there is elastic and plastic ranges. The region in the stress strain diagram from O to P is called as elastic range, and region from P to R beyond the elastic limit is called as plastic range. And then I define yield point. On the curve, yield point is the point at which the material will have an appreciable elongation or yielding without any increasing load. So, at this point we call it is a yield stress. So, and then ultimate stress, ultimate strength. The maximum ordinate in the stress strain diagram is the ultimate strength or the tensile strength. So, at the ultimate point is called as ultimate strength. And then is rupture strength on this curve. Rupture strength is the strength of the material at rupture. So, this is also known as the breaking stress, breaking strength. And then I will define modulus of toughness. Modulus of toughness means is the work done on a unit volume of material as the force is gradually increasing from O to R. So, this may be calculated as the area under the entire stress strain curve from O to R. The toughness of the material is its ability to absorb energy without causing it to break. That means specimen absorb maximum amount of energy before breaking. This is called as modulus of toughness. And then I will also define modulus of resilience. So, modulus of resilience is the work done on a unit volume of material as the force is gradually increasing from O to P. This may be calculated as the area under the stress strain curve from the origin O and up to the elastic limit point. So, the shaded area in the from elastic region from O to P. So, the resilience of the material is the ability to absorb energy without creating a permanent distortion. So, without distortion the specimen absorb maximum amount of energy is called as resilience of the material. And then I define working stress, allowable stress and factor of safety. First, on the stress strain curve, we calculate the working stress. Working stress is defined as the actual stress of the material under the given loading. The maximum safe stress that a material can carry is termed as the allowable stress.